All right, hello everyone, and welcome to our session that is supported by the Statistics and Data Science in Aging Interest Group. We're not officially a part of the American Statistical Association yet, but hopefully we will become a section in the future. Our group is fairly new. We're in our second year of existence, and we have lots of great plans. So hopefully this isn't getting cut off. It's a little cut off on mine, but basically our goals of the Statistics and Data Science in Aging group is to connect researchers in quantitative fields working in aging for both research opportunities, career development, networking, collaboration, and to try to really facilitate sharing opportunities. And we're especially interested in having people across the career spectrum, so early career all the way through the end, so that we can all help each other and work together in the field of aging. So if you're interested, oops, sorry about that. If you're interested in joining our group, here's a QR code that links to our website. It's free to join, and we don't spam with too much email. We have a very active webinar program. So once a month, we have a research talk. And as well, we have other programs for early career faculty and researchers and industry statisticians. We have meetups at conferences. And honestly, it's just a really fun group. Everyone is absolutely great. Our executive committee is going to be doing elections soon. So if you're interested in joining, then please go to this webpage and join our email list so that you can be in the know for our upcoming events. And so I probably should have also mentioned I'm the program chair right now for our group, but I'm also giving the first talk in this session. So to briefly introduce myself, I'm an associate professor of biostatistics and data science at Wake Forest in the School of Medicine. And today I'm going to briefly be talking about some of the methods that I've worked on with machine learning approaches for longitudinal data analysis focused on predicting mobility limitation in older adults. And the main area of my work is clustered and longitudinal data. So probably, as you all remember from your statistics courses, when we have longitudinal data, or the more general term is clustered data, our outcomes are correlated or form some sort of dependency structure. So a very common type of longitudinal analysis that we see in aging studies is when we have outcomes that are collected for a patient or participant at many time points, or some people also call this repeated measures. But the more general term is clustered data, which is just when outcomes are correlated within some sort of group. So examples of that might be families, or a hospital or study site might be a group that has some sort of correlation structure. These are very common in biomedical research, and especially in studies of aging, where we're collecting data on people across time. And so you'll probably also remember that a typical way that we analyze clustered and longitudinal data is using a generalized linear mixed model. So here we have our outcome Y, which is connected by a link function G to our linear effects for predictors. And then we also have random effects, which can then adjust for the clustering or correlation in our data. And over the past, I'd say about 2 decades, some of the work in the machine learning and AI world has involved extending these generalized linear mixed models for machine learning and AI methods. So you can kind of think of the main idea behind a decision tree method would be, instead of using linear effects in that middle term, we would try to incorporate in some way having tree effects or random forest, or you could kind of throw in any type of model into that, such as like neural networks or boosting. But the main idea is taking this generalized linear mixed model framework and extending it for these machine learning and AI methods. And then we get the best of both worlds. So over the past 2 decades, these methods have become very popular. And so here I'm just kind of listing out some of the newer and traditional methods and the R packages, and then the different outcomes that they're available for. So some of the early work in this area focused on continuous outcomes, mainly because the computation was a lot easier. With a generalized linear mixed model, you have closed forms for estimating all of your random effects. Binary outcome and multi-class outcomes came later because it's a bit more challenging, because you don't have that nice closed form for getting those estimates. But this is just to show there's lots and lots of methods out there. And I was one of the first to really look at focusing on binary outcomes. And back in my dissertation work, I developed something called the binary mixed model algorithm, or BIM algorithm, which is basically where we do some model. So it could be a decision tree or a random forest, neural network, whatever you want to put in there. And then we take the outcome from that model, so the predicted probabilities for each observation, and we put that into a generalized linear mixed model as a predictor. And then at that stage, we can incorporate the clustering effects through random effects. And then we use a kind of expectation maximization algorithm to update the outcome and iterate through those steps until we get convergence. And the unique factor with the BIM method is that the generalized linear mixed model is applied in a Bayesian setting. And the reason that we chose to do it like that is because it gets around some of the convergence issues that can happen with frequent test methods. So initially, I developed a method called BIM tree, which was a decision tree method, and then later extended that to random forest with BIM forest. And then when I started my faculty position, I added on variable selection to the method as kind of like a pre-step. So using packages already developed, which will select variables that will then go into that BIM forest algorithm. But really today I wanted to focus on the application side of it in aging. So our Wake Forest University has an excellent Pepper Center, which is focused on aging research. And a lot of the problems that they're working on are surrounded by mobility in older adults. So here I'm showing a Sankey plot of mobility limitation in older adults over time in the Health ABC data set. So as you can see, the older adults go in and out of these states over time. And in general, as the study goes on and as these people are aging, more and more people have mobility limitation. And really, all of the prediction models that are in the literature don't use this repeated measures data. So my goal was to develop some models and compare them and try to find, which methods would be best for predictions in this setting. So we did 4 models. The first was a BIM forest with all the predictors that we included. Model 2 was a BIM forest with that variable selection included. And then models 3 and 4 were the BIM forest and a generalized linear mixed model with just the top 5 variables plus age. So that was really just to try to keep it as simple as possible. We included a whole bunch of different predictors for modeling. These included fixed predictors as well as yearly collected predictors. Everything from demographics to lifestyle, medical history, as well as, things that are routinely collected at doctor visits over time. And basically, so before I get into the results, the other thing I wanted to mention is that when you have repeated measures data, you have to be really careful about how you split your data into training and testing data. And so here, the way that we decided to do it was we included data up until the last observation for every participant in the data set in the training data. And then our testing data set was the last observation that we had for each participant. And so that way, the interpretation of the prediction model would be predicting out future mobility limitation using, past observations, so that the idea would be that if you predicted that someone would have mobility limitation in the future, that you would try to intervene on it and try to prevent that from happening. Okay, so as it turned out, all of our models performed remarkably similar. The main difference was the number of predictors that we included in each model, and that was specified based on how we did the variable selection. But overall, the performance was extremely good. The area under the receiver operating curves were 0.81 to 0.84, and all of the confidence intervals overlapped, as you can see in these plots. So basically, we were very encouraged with this prediction model and hope that it can be useful for potentially trying to find older adults who may be at risk for mobility limitation in the future. So to summarize, the focus of my work is longitudinal repeated measures data. And here we were able to develop some pretty accurate prediction models for mobility limitation in older adults. Currently, I'm working on incorporating missing data imputation into the BIM forest framework. It's been a bear of a project, but hopefully it'll come out soon. And I wanted to conclude with why I love working in aging research. You know, from a data side, I feel like there's lots of interesting problems with longitudinal data, and it's just challenging and fun from that side. But also, it really, to me, has very meaningful impact. You know, we live in a world where everyone is aging, you know, and hopefully everyone will have the blessing of becoming older and experiencing aging. So it's really meaningful to me to work in this area, you know, and really make an impact in medicine. So that's my spiel. I'd like to thank all of my collaborators and funding mechanisms. This QR code is a link to my website. Also, I have a bunch of code on GitHub. So if you're interested in learning more, please go there or reach out. And I think hopefully we should have time for questions at the end of the session. So at this point, I'm going to transition over and introduce our next two speakers. So we have Siting Chen and Alicia Feryn are biostatisticians with Biostatistics and Design program at Oregon Health and Science University. Siting specializes in quantitative methodology for health science research with expertise in longitudinal modeling, survey data analysis, and geriatric and aging research. Alicia's interests focus on mortality, aging, and longevity, with particular emphasis on proteomic predictors, and more recently, the frailty phenotype. So Siting and Alicia, thank you so much for joining us, and you can take it away.
Awesome, thank you, Jamie. As Jamie mentioned, I'm Alicia Feryn, and I'll be presenting with my colleague, Siting. We'll be sharing our analysis of frailty trajectories and the relationship to longevity using data from the Health and Retirement Study. Our work is supported by the Longevity Consortium and the National Institute on Aging. Next slide, please. The HRS is a longitudinal panel study of US adults over 50, collecting rich data on health, economics, and family. Each cohort is interviewed every 2 years. For our analysis, we use data from waves 8 to 16. Next slide, please. Which corresponds to years 2006 to 2022. And our analysis is focusing on participants aged 65 and up and excluding those in nursing homes. Next slide, please. Our outcome of interest is the frailty score, which was derived from a modified version of the original Fried frailty index. This phenotype includes 5 domains: shrinking, poor energy, low physical activity, slowness, and weakness. Unlike the original Fried frailty index, we use hard thresholds for slowness and weakness rather than quintiles. These domains are scored as present or not, and sum to create a score from 0 to 5. A frailty score of 0 indicates not frail, 1 to 2 is pre-frail, and 3 or more is frail. The top panel of the graphic on the right shows the sample size across the age distribution, which decreases with age. And then the panel below displays the proportion of individuals with each frailty score across age. We see that lower frailty scores decline with age, while higher scores become more common. Next slide, please.
I'm going to talk about the statistical analysis. For this analysis, we estimated frailty score trajectories using latent class mixed models. This method allows us to identify distinct groups of individuals who follow similar frailty patterns at their age. Compared to traditional group-based trajectory modeling, the LCMM extends the framework by allowing for within-group heterogeneity. So it doesn't assume that everyone in the group follows exactly the same path, which means people within the same group might have varying random slopes and intercepts, which makes the trajectory prediction more flexible. We also considered several criteria for model selection, including fit statistics such as BIC, the relative size of each group, the average posterior probability of class membership, and importantly, the clinical interpretability of the resulting groups. To ensure reliable trajectory estimation, we only included individuals who contributed at least 2 frailty score observations over the entire study period. Once we identified these trajectory groups, we used multinomial logistic regression to examine how individual characteristics were associated with membership in each trajectory group based on their modal assignment, which means the individual will be assigned to the group with the highest probability. Finally, we evaluated age and death and the longevity outcomes across the trajectory groups in order to understand how different frailty trajectories are related to survival. Next slide, please. This figure shows the 4 identified distinct frailty trajectories from the results of our latent class mixed model. You can see in the middle of the figure, the dashed line at a frailty score of 3 is the threshold for frailty. The 3 groups start with relatively low frailty at age 65, but they follow very different paths. First, if you take a look at the robust group, it starts with the low frailty around age 65 and stays relatively low and stable throughout the early years, and only shows modest increases in frailty into their late 80s and 90s. If you look at the pink group, the gradual progressors, it starts at a low frailty level 2, but then it steadily increases across the late life course. This group represents the largest proportion of the study population. It shows a slow but continuous accumulation of frailty. If you take a look at the rapid accumulator group, the green group, it begins with low frailty, but it shows a very steep and rapid increase, surpassing the other groups really quickly and reaching the higher frailty scores by the 80s and 90s. Finally, the purple group, the neo-frail group, it starts out at a higher baseline frailty score, and it stays relatively stable across time, showing less change compared to the other groups. Overall, these trajectories highlight the substantial heterogeneity in the way frailty develops with age. Next slide, please. Then we look at the baseline characteristics by frailty trajectory group. These figures show the proportions of different categories of sex, race and ethnicity, education, wealth quartiles, couple status, and nativity across the 4 identified trajectory groups. You can see from the figure that the gradual progressors and robust group has a higher proportion of non-Hispanic white people. The near-frail and rapid accumulators has a higher proportion of non-Hispanic Black and Hispanic people. If you take a look at the education and wealth, you'll notice that higher education level and higher wealth quartiles are more prevalent in robust and gradual progressors. And there are no evident differences in sex, couple status, and nativity across the 4 groups. Next slide, please. Then we conducted a multinomial logistic regression of frailty trajectory group membership, including these characteristics. This forest plot displays the odds ratios and confidence intervals for factors associated with membership in each frailty trajectory group when compared to the robust group. You might notice that people in minoritized racial and ethnic groups and the people with lower education attainment, lower wealth are more likely to follow the rapid accumulating path and the near frail path of frailty when compared to the robust group. Next slide, please. This table basically summarizes the survival outcomes across the four frailty trajectory groups. If we look first at the median age at death, we can see a gradient. The robust group lived the longest with a median age of 88, compared to 86 for gradual progressors and just 81 for both rapid accumulators and near frail groups. If you pay attention to the box that I highlighted here, the proportion who survived to age 90 in the robust group, nearly 23% reach at least age 90. Among gradual progressors, the number drops to about 15%. For the near frail group, it's only about 10%. And in the rapid accumulators, survival beyond 90 is the lowest. It's just 4.7%. So this highlights how different frailty trajectories are associated with longevity, particularly survival into advanced ages like 90 and beyond. Next slide, please. This fancy figure shows a Kaplan-Meier curve by frailty trajectory group. As you can see, the individuals in the robust group have the highest survival probability across age, followed by gradual progressors, and then near frail and rapid accumulators. The separation between these curves indicates that those with more severe or rapidly progressing frailty may experience earlier mortality. Overall, this demonstrates a clear gradient in survival associated with frailty progression patterns. Next slide, please.
So lastly, we wanted to touch on our next steps, which are to incorporate polygenic risk scores, biomarker data, and time-varying health-related characteristics into these models. We'd also like to harmonize the frailty phenotype and apply these methods to other studies. So this table illustrates that process of harmonizing the frailty phenotype in other studies, such as Mr. Ossoff and Health ABC. Next slide. And lastly, we'd like to thank everyone involved in this project. We're grateful for the opportunity to contribute to aging research. Working with these rich longitudinal data sets is especially rewarding, not only because of the analytical challenges they present, but also because of the chance to help improve the quality of life across lifespan, particularly in later years. And that's all. Thank you.
Awesome. That was a great presentation. Okay, so next up we have Dr. Zheyu Wang, is an associate professor in the Division of Quantitative Sciences at Sidney Kimmel Comprehensive Cancer Center with joint appointments in the departments of biostatistics and applied mathematics and statistics at Johns Hopkins University. Her research focuses on developing and applying statistical methods to improve diagnostic accuracy and reduce diagnostic errors in healthcare. And she is our incoming chair for the Statistics and Data Science and Aging Interest Group. So Zheyu, we're very excited to hear about your work.
Thank you, Jamie. Yeah, as Jamie mentioned, that I'm an incoming chair for our interest group. So I very welcome anyone who will be interested to join this group. Currently, we has been an interest group for 2 years, and we plan to become a session next year. So today I would like to talk about my work using joint model of multivariate biomarker trajectory to do AD prognosis, Alzheimer's disease prognosis. So as many of us know that Alzheimer's disease is the most common form of late life mental failure and the 6th leading cause of death in the US. We actually have one case every minute, so it's quite a big issue. And compared to all other diseases whose incident, the prevalence has decreased because of therapeutic advancement. The prevalence for AD and deaths from AD has increased more than 100%. And one of the issue is that AD prevalence increased dramatically with age, and now we have an aging population. And the other thing is because AD has a long preclinical phase where patients appear to be cognitively normal, and when they have noticeable clinical symptoms that warrant a disease diagnosis, their brain structure has changed too much that there is no effective treatment to reverse that change. So therefore, the current emphasis in the field is to do early diagnosis, and early diagnosis will require the use of multiple biomarkers. Next slide, please. Because as we mentioned, these patients are appear to be cognitively normal. So what we can detect is the biomarkers inside their brain and in the cerebral spinal fluid, or use MRI biomarker to reveal potential pathological change. Next slide, please. So a key hypothesis using AD research is this Jack hypothesis, which this is the different curve are different biomarkers. It's trying to depict the order and sequence and shape of different biomarker evolution along the disease pathway, so that we can, by observing this biomarker, infer the underlying disease trajectory. But as I mentioned, it's still, even though it's used in many research, but it's still a hypothesis. One of the issue in validating this work is the use of this axis, like the currently, next slide, please. The axis is in clinical disease stage. And as we mentioned, this is unknown before symptoms become noticeable. And also there are great heterogeneity in patients. For example, as the prevalence increases dramatically with age, so age is a big confounder in this plot. So there is an alternative modeling attempt using age, or use time from prior to symptom onset as this axis to attempt to address this confounding issue with age. Next slide, please. And that promote the updated Jack hypothesis. He actually changed the original labeling from clinical disease staging to time, but he also emphasized that the time is not necessarily calendar time. In fact, it need to recognize individual heterogeneity. And Jack in his paper specifically mentioned these two terms, that one is should characterize it has this this time has a subject specific scaling and shift of time. And another phrase he used is very interesting, as a distance traveled along the pathophysiology pathway. So to a statistician, these two comments leads to two common statistical approach. The first one will be a random effect model with like a random shift or random slope. It's a subject-specific random effect. And the second one will lead to a latent variable model, just similar to the talk in the second talk. But here we consider the latent variable as a continuous progression that reflect the continuous disease. Next slide, please. So in trying to determine well, which of the two directions I'm gonna pursue, the first thing is if I want to pursue the first one, meaning I want to specify random effects, I want to see what kind of mean model and what kind of random effect pattern that I should use. So I plot a spaghetti plot of different of one biomarker. So, but I plot all of them. But this plot is one of them. Against time from symptom onset to see, oh, is there any pattern I can see what kind of random effect I should use. As you can see that I cannot see a clear pattern. And alternatively, next slide, please. When I aligned the biomarker against a just simple latent variable model that reflect the disease status, you can see the different group. The group are kind of different risk factors. Different group are more separated, and then the pattern become more clear. So this is my reason to pursue the second approach using a latent variable modeling. Next slide, please. So now that we determined our modeling approach, we model the latent disease D as a function of individual covariate, so that the disease progress is can depend on like age, gender, ApoE, etc. And biomarker then similar to what Jack hypothesis is a S-shaped curve, like in the F term. The F is a S-shaped curve of the latent disease. And then we also have covariate in the biomarker that can be like, for example, normal aging effect that still also affect biomarker, but is separate from the latent disease. And we use logistic curve here because it's for its parametric model is more efficient, and also because it has a nice interpretation that we have the height of the curve, and we can find how steep the curve is going up, and also the midpoint that allow us to see the ordering of different progression. And the choice of parametric model is because in AD study, we don't have a lot of repeated measurement. So use a non-parametric approach, even though it may be more flexible, it may have like your confidence interval may be too wide to do any inference. That being said, next slide, please. We recognize that logistic curve, even though it reflects a range of S-shaped progression, it is a symmetric curve. So we also tried this piecewise logistic, basically piecing two logistic curves together so that it can have a asymmetric shape. Some biomarker can progress slowly initially and then speed up towards the end. And the nice thing about this piecewise logistic is it's actually twice differentiable at the point where the two curves join. So all the asymptotic and property are still holds, even though it appears to be a piecewise curve. Next slide, please. So here are the results we do with this model in the biomarker study, which is a study following 300 cognitively normal patients, and now it's almost 3 decades now, to see different trajectory progress. As the top one is use a logistic curve, and then the bottom one you use the asymmetric, the piecewise logistic, and you can see the ordering are quite similar. There are some shape change, but the order in general are similar, with the first group of the CSF biomarker followed by the MRI biomarker, and then some cognitive assessments. So it's relatively consistent with what the hypothesis sequence in the Jack model. Next slide, please. So now that we have this model, another thing we want to think is that we're doing real data analysis, and because AD has such a long time frame, like it takes decades for people to progress. Are we sure that our study covered the entire trajectory of this biomarker progression? So if we don't, then maybe it will have a biased result. So we plot the estimated disease time of our data, and we do see that most of them are in the initial phase because these are recruited as cognitive normal patient, and there are very little data go to the end of the curve. So if that's the case, then there is a chance that because we use this as parametric model, is assuming we observe all the data, then it could introduce bias. Next slide, please. So how we address this intuitively, like if we know the height of the last progressing biomarker, then we should be able to correct this. And that's what we tried. In simulation, we show that if we know the height of the biomarker, then everything can be corrected. In fact, we can only, as long as we know the last one, then we have correct estimate. But if we know more of the height, then we can improve efficiency. And practically, this approach is feasible because the last progressing markers are those cognitive tests, and those are standard tests. We know their range, and they have been studied in many different populations. Normal, it's well studied for years. So that gave us practical feasibility to use this approach. And we also assess because if your height, just potentially if your height is specified with some kind of error, we use simulation to see how much that will affect our result. And you can see actually both the bias and coverage are pretty good. Next slide, please. So that's all of my talk. Would like to thank the grants work that support this work, and also the BioCast study and any study. And thank you all for attending this talk.
All right, thank you, Zheyu. Really, really interesting work. Okay, and our next speaker is Julia Gallini, who is a PhD candidate in biostatistics at Boston University. Her research is focused on longitudinal modeling in neurodegenerative diseases, including Alzheimer's, dementia, and Parkinson's disease. Her methodological interests include state space models and joint longitudinal survival models. Julia is one of our Statistics and Data Science and Aging interest group ARISE finalists, which was a program that we launched to give early career researchers an opportunity to share their work. So congratulations on that, Julia, and we're excited to hear about your research today.
Okay, can you hear me now?
Yes, we can hear you.
Perfect. So I'm going to be talking today about cognitive factor-based selection, increasing power in Alzheimer's dementia randomized clinical trials. And you can go to the next slide. So this is a brief outline of what I'm going to discuss today. Next slide. So for some background, Alzheimer's dementia, or AD, is the most prevalent form of dementia worldwide, and it's becoming more common as populations achieve longer lifespans. And there remains a substantial gap between the supply and demand for safe, affordable, and efficacious AD treatments. Ideally, AD drug trials would enroll cognitively normal participants to test the efficacy of a drug at preventing AD symptom onset altogether. But AD trials among cognitively normal participants are often very underpowered due to a low number of AD events. And so often these trials resort to enrolling participants that are already at the MCI stage, or mild cognitive impairment. Next slide. So the motivating question for this research was, how do we improve power in AD drug trials for cognitively normal participants? Next slide, please. For some more background, predictive modeling for AD trials to enroll high-risk subjects has been proposed by Azadi et al., but not implemented. And previous enrollment criteria in these trials, and also including the Azadi paper, require imaging and PET scan data, and this disproportionately excludes populations without healthcare, as well as racial minorities in the US. And so we're proposing the use of predictive modeling based only on cognitive factor scores and baseline covariates to improve power in AD trials, while also hopefully limiting the exclusion of these underrepresented populations. And our novel longitudinal factor model provides many statistical and clinical benefits over other predictive modeling options to enroll high-risk participants into these trials. Next slide, please. So for an overview of the methods, we first derived 4 statistical factors. The factors were memory, language, working memory, and psychomotor speed from 10 standard cognitive tests using our novel longitudinal factor model in a state space model framework. And I'll talk more about that model specification in a moment. After that, we developed a predictive model of 3-year AD risk using the cognitive factors that we derived in step 1, as well as some baseline covariates, and this was all done using NAC data. We then simulated 10,000 randomized controlled trials for varying treatment effects under 3 different subject selection methods: a truly random selection using our cognitive factor model to select high-risk participants, and then finally using a covariate-only model to select high-risk participants. Our main results in step 4 are to compare power and required sample size across these 3 selection methods. Next slide. So this is the model specification to derive these cognitive factor scores, and I'm going to talk through each component of it since it's a little bit complicated. Next slide, please. So our Ys in this case are just our standardized cognitive tests. We used 10 for this particular application. These are very simple tests that are given at any sort of memory care visit. They are things like connect these dots in order, draw a clock, relatively straightforward tests that are very accessible for the general population. Next slide. G is just our factor loading matrix, so it's transforming factor scores back into the cognitive test scores, or Ys. And an important benefit of this model is that G is actually directly estimating the correlations between the cognitive tests and the statistical factors, so it's giving us some clinical estimates of interest. Next slide. Alpha is the main component of interest from this model for this particular application. These are the actual cognitive factor scores that we're deriving. We have 4 for this application. Those are the memory, working memory, psychomotor speed, and language factor scores. And what makes this model specification a state space model is the way that we're handling the estimation of the alpha. So the first line of the equation that I've been talking through so far, the Ys equal G alpha, etc., is called the measurement model, and that's a pretty standard factor model. What makes this a state space model is the second line of the equation, which is the state equation, and that's where we define that alpha I at time point j is going to be equal approximately to alpha I at time point j minus 1 plus a random walk component. So we're basically saying that because we're working with a cognitively normal population, we're expecting an individual's cognition to remain relatively stable over time, but we are updating the factor scores at each time point such that they can progress non-linearly if need be. And we're going to use this parameter later in our methods when we're actually trying to predict probability of conversion to AD. Next slide, please. Epsilon is just an error term. We can estimate a covariance structure for it. Next slide. And our etas are also an error term. We can estimate a covariance structure. We can also directly estimate the correlations among the factor scores themselves over time while allowing for unequally spaced observations given the structure of this error term. Next slide. So the model estimation, we estimated it using a Gibbs sampler, so a Bayesian framework. I'm not going to read through all of the steps for the sake of time, but in general, we are estimating each parameter from its conditional posterior distribution, and those distributions are going to be conditioned on either the prior for the other parameters on the initial run through of the sampler, or the updated estimate of each parameter. We repeat these steps over and over again using the most recent estimates of the unknown parameters each time until these estimates have converged. And then we take the mean of the non-burn-in samples as our final parameter estimate. Next slide. So we ran the Gibbs sampler through 10,000 iterations. At that point, our model estimates had converged well. So now that we'd estimated cognitive factor scores, or the alphas, in that model specification, we began to use these scores in predicting 3-year conversion to AD, and we picked 3 years since that's the approximate length of most of these clinical trials. Next slide. So using NAC data, 1,700 subjects were randomly selected for the training set. We just fit a logistic regression model to predict AD, a probability of conversion to AD. So this predictive model is quite simple. We're using all 4 cognitive factor scores as predictors, as well as this list of covariates, known things to be associated with development of AD. And then we calculated the probability of AD in 3 years for each subject from this logistic regression model. Next slide. For the trial simulation, we had 4,500 subjects approximately forming the test set. All of them had 2 cognitively normal visits, and we used their second visit as their baseline trial visit. For a random selection, we just took 1,000 subjects with replacement from the full test set, and that was the trial set for that iteration. For factor model selection, we were again selecting 1,000 subjects with replacement, but this was from a high-risk subset of the test set. And that high-risk set was determined by taking everyone whose probability of conversion to AD was greater than 0.15, using that predictive factor model. For covariate model selection, it was very similar to the factor model selection, except instead of using a predictive model that contains those cognitive factor scores, we are only including the baseline covariates as predictors in this model. So we get a slightly different high-risk set using that prediction method. And then subjects were assigned randomly with p equal to 0.5 to treatment and control groups. We ran 10,000 iterations of each selection type for treatment effects ranging from 0.05 to 0.5. Next slide. So we're planning to use a Cox proportional hazards model to analyze the trial data. So we needed to derive a censoring status variable and a follow-up time variable for every individual. So first we looked at what actually happened to the individual in real life. AD converters before 3.5 years after their baseline visit, we just took their time to first AD visit as their follow-up time, and they would be considered an event. Non-converters were censored at their visit closest to 3 years from baseline. Subjects that died during the study window were censored at their date of death, and subjects that did not have a visit after their baseline visit were considered lost to follow-up. Next slide. We could then calculate the trial outcome, or what might happen to these individuals in a hypothetical trial based on what happened to them in real life. So everyone in the control group would keep their true outcome and follow-up time, as well as true non-converters in the treatment group. All of their data would stay the same. The people that stood to benefit from the trial were the true converters in the treatment group, and they were assigned a new random outcome drawn from a binomial distribution with p equal to 1 minus the treatment effect. And then we changed their follow-up time to 3 years if the treatment worked. Next slide. So these are our results. We're looking at the median power over 10,000 simulated clinical trials. In green, we can see that the factor model selection is outperforming the covariate model selection in red and the random selection in blue across our range of treatment effects along the x-axis. Most realistically, we're going to see treatment effects between 0.2 and 0.4. And so that's kind of the area we like to focus on to see if this is actually greatly improving our power, and we determined that it is. Next slide, please. On the flip side, we can look at the median number needed to recruit for 80% power. At the low treatment effect sizes, we're seeing pretty unrealistic numbers. It's not really realistic that we'd be doing a trial for a treatment effect that small. So again, focusing on the zoomed in portion of the treatment effects between 0.2 and 0.4, we are seeing realistic numbers of participants that we would need to recruit using the factor model selection and the covariate model selection. And we are seeing a difference of several hundred participants between those green and red lines, despite the scale of the y-axis making them look pretty similar. Next slide. So to summarize, our longitudinal factor model is directly estimating latent cognitive factor scores, their correlation with original cognitive tests, and the correlation structure of the factors themselves over time. Trial selection based on our cognitive factor model greatly improves power and number needed to recruit over alternative selection methods. We did not use any imaging data for this method, so we would expect that it would be more inclusive of underrepresented groups and trials. But a major limitation of this work is that the cohort used is predominantly white. And so we would definitely want to replicate these findings in a more racially diverse cohort to ensure that we're seeing the same type of results in our target population. Next slide. I'd just like to acknowledge my advisor, Yorgos Tripatis, as well as Zach Baucom, whose dissertation work inspired this project. It's been great to work with both of them. And next slide. Thank you so much.
All right, awesome. Thank you so much, Julia. Your PhD work is amazing, and I feel like you're going to do great things in the future. So I just wanted to have this slide up again. Here's the QR code if you're interested in joining our statistics and aging and data science group. And I guess I don't see any questions in the chat, but if the people viewing have some questions, then please write them in. I'll get it kicked off with kind of just a basic one, but so we all work in aging. You know, some of us are more focused on like aging and disease and function and the kind of general health of older adults, and some of us are in Alzheimer's disease and specific disease areas. So I'm curious for all of you who just shared your amazing work, how did you get started in the aging field, and like what opportunities do you see for, you know, people who haven't worked in this area to get involved?
I can start. I really enjoy how little we know, to be honest, about a progression of aging. There's so much heterogeneity, as we saw in basically all of the talks this evening, in how people progress. And it really opens the door for a lot of diverse statistical methods to try to parse through what's happening to these different subgroups in an attempt to predict clinical progression. And so it just felt like a great area to me where it's just there's no shortage of methods to be applied and to experiment with, and that's why I got into it.
Yeah, awesome. Thanks, Julia.
I can share. So when I first started my work at OHSU as a biostatistician, I got one opportunity to join in a research group. Anna Cunions, she's a really great investigator at OHSU focusing on aging research, and I have the opportunity to work with her on looking at the racial and ethnic differences in multimorbidity progression and dementia outcomes and the cognitive impairment change for older adults in United States. So that's the first time um, when I get in touch of this area. And then I also work with other co-investigators and scientists at OHSU and across different universities and institutes on looking at the biomarkers and their associations with aging. That's also one of the major area that I'm currently working on. Yeah, so this is where I first get into this topic and explore my interest.
Yeah, awesome. Biomarkers are so big in aging right now.
Yeah.
I feel like, yeah, there's a huge opportunity, especially with the new technologies that are allowing them to be measured. And, you know, like the high dimensional data problems are real, and, you know, it's fun to get to work on those.
Mm. Yeah.
Yeah, I can share next. I first got into aging-related research. I think it's when as a graduate student, when I was a research assistant working in the National Alzheimer Coordinate Center. So I got into the research of Alzheimer's disease and other like aging-related topic. I think even though like initially it just kind of happened to me, but I really enjoy this line of research because for disease there are many therapeutic approach, but aging is just so heterogeneous, and every one of us is aging. like you can avoid some disease, but you can never avoid aging. So it's just like really like what to yeah, it's a experience. So yeah, and I feel yeah, we have all the different aspects regardless what you're working on. We can do trials that's has aging related component, or we can have like observational studies. So any topic you can think of, I feel this is just a like a treasure box.
Yeah, I think something else that has been really cool too with our group, seeing just how many innovative methods and study designs are being worked on in the specific area, and then that, you know, other domains can also borrow from. So I think that's really cool.
I can jump in too and mention that. Yeah, I've been working, or I got into studying aging when I first got connected with the Longevity Consortium. I've been working with them for about 4 years now, primarily looking at associations between proteomics and longevity or mortality, and looking at that. And then in my other work, I've looked at other kind of aging related diseases like Alzheimer's. And so it's cool to see the overlap. That's kind of why I like to be in this field, is like seeing the overlap between these diseases and the implications long term, and kind of the different kind of predictors that come up for all the different diseases. Has been really cool to see that.
Yeah, awesome. Well, I think we're coming up to the hour, so I just wanted to again acknowledge our speakers, Julia, Alicia, Sitang, and Zheyu. Amazing work that you all are doing, and really excited to see where you all end up in terms of your work. And thanks for participating today. And remember to join our group. It's the Statistics and Data Science and Aging Interest Group. We have a website. And membership is free, so get on our email list, and we hope to see you at some of our events.